Hello, class. This is Paul DiStefano. I hope you're all doing well. After reviewing submissions for Module 4, specifically question 6-3, I decided to post this video to actually run through how the solution is charted in Excel for an X bar and an R chart, and how the additional data is measured against that chart to determine whether the process is in control or out of control based on additional observations. So if you look at your screen, you'll see in Excel the data is put in a table here. There are 6 service personnel, and each person is observed with customer 4 times. I changed this from observation to observation 1, 2, 3, and 4 instead of sample 1, 2, 3, and 4, because that's kind of confusing when you see 4 samples up here and you see 6 service personnel and it's a sample size of 6. I just want you to know that each person is a sample, and multiple observations of a person does not make additional samples. Otherwise, you could use one person and observe them 1,000 times and think you had statistically significant data with 1,000 samples, but you really don't, because you only have one sample size. So in this case, there are 6 sample size of 6 with 4 observations each for a total of 24 data points. Sorry for that. You probably heard my phone ringing in the background, so I shut it off and I'm back. So getting back to the sample size of 6 with 24 data points, the first thing we do is we calculate X bar, which is the average of each observation across the 6 samples. So the average of these data points is 116. This is in seconds, by the way, even though there's no units of measure shown on here. The average of this observation, the average of this observation, and the average of this observation. So what you'll see is that X bar is an average. X bar bar is an average of the averages. So it's a mean of all the data. So what they did, they calculated it by taking the average of all these, and you can see down here that's 116.42. What that essentially is the average of all the data points, because it's an average of an average. So if you were to highlight this and look down below, you'd see the 116.42 again. So that is the mean for the entire data sample set. Next thing we do is calculate the range, which means we take, for each observation, we take the max minus the min, and we get 132, 85, 100, and 100. Essentially, the 200 minus the 68 here gives you the 132. Then, of course, we already talked about X bar bar, which is the mean of the means. So it's the average of the entire data set. I hope that's not confusing. If it is, contact me and we can walk through that again. R bar, of course, is the average of the ranges. So if you look at this right here, these 4 data points, you get an average of 104.25 down here below, so that's where the 104.25 comes. You can use the Excel formulas, or you can just use the bottom of the screen where it has the common functions of sum and average. So now, getting to how we plot this data, if you look at X bar, 116 comes directly from here, 105.5, 124.17, 120, and then 120. The center line is essentially the mean average of all the data. So the 116.42 goes all the way across, and that's the center line. Because it's an X bar chart, the center line should be the average of all the X bars, which in this case is X bar bar. The lower control limit are then calculated using the formula you see right here, B10, which is X bar bar minus 0.483 times D10, which is the range. So you're taking the average data times 0.483 times the total range of the data. And the 0.483 basically comes from table 6-7 for a sample size of 6. So the lower control limit is how far below the mean you can be and be in control for a sample size of 6, meaning that you're 3 standard deviations below the mean. And then the upper control limit, you notice the formula is just plus 0.483, which is 3 standard deviations above the mean. So if you're familiar with statistics and bell curves, plus and minus 3 standard deviations you might have heard as 6 sigma. Plus and minus 3 sigma is 6 sigma, and 6 sigma represents 99.7% of the data for an in-control process. Data outside of that would show that your process is not in control if you keep on experiencing outliers like that. So then to chart this, we will highlight the data, including the axes titles that we want, the legend, and we will right-click on that data, and we will say Insert 2D line chart, and the one we want is the line with markers, and voila. I did it up here already, but I thought I'd reproduce it so you can see exactly what I clicked on to get it. If you don't get it in this exact format, sometimes you have to switch the X and Y axes to get it with the samples along the bottom and the data range along the Y-axis. So let me delete that since it's up here anyway. And as you can see, here is the upper control limit plotted, the lower control limit plotted, the center line plotted, and like I said before, since it's an X bar chart, the data points are the X bar, the mean numbers, but the center line is the mean of what the chart is, which means it's the mean of the X bar or X bar bar. Just like if you come over here to the art chart, the mean is the average range because you're plotting the actual range data points. But back to this one, I just wanted to show you that based on the chart title and how you're what you're plotting shows you what the mean is. So then the upper control limit 3 sigma above the mean X bar, and lower control limit 3 sigma below the mean X bar, which is X bar bar. Sounds confusing, but once you get used to it, it becomes very obvious. So the next thing we'll do is the data for the range chart. So you can see, if I can get the whole thing on the screen here, the ranges are 132, 85, 100, 100. They're transposed down here, or transcribed, I should say, just so we get them on one table for charting purposes. The center line is R bar because you're plotting the range, so the center line has to be the average of all the ranges. Then the lower control limit, of course, is 0 because the range can't be less than 0. Sometimes in the calculations using the formula, you'll get a slight negative number, but you should just put 0 in there whenever you're getting a 0 average or a negative average or a negative range. Then, of course, the upper control limit is the R bar, the average range, times 2.004, which you look up on table 6-7 for a sample size of 6. So then we essentially do the same thing. We calculate or plot the R chart using this data and using exactly what I did before. Let me see if I have to swap X and Y on this one though, so I'm going to do it again. Highlight the data, insert a line chart, use a line with markers, and I do not have to swap the X and Y as you sometimes have to do. So it basically plotted the R chart here. It's a little bit more scrunched because I think up top I spread it out a little bit. You can basically do that for charting purposes on presentations, is change the size of it by dragging the corners or the sides. So let me delete that now. So as you can see, you have the mean R, which is R bar, as your center line. You have 3 sigma above it, and you have 3 sigma below it. 3 standard deviations above, 3 standard deviations below, and then what you actually plot is R. Just like over here, what you actually plot is X bar. And that's going to become important when you look at the follow-up question, which is, let me go over here to read it. Says, after the control chart was established, a sample of 6 service personnel was observed, and the following customer service time in seconds were recorded: 180, 125, 110, 98, 156, and 190. So I already put these down here just for calculation purposes. So what would the X bar look like for a data sample set that looks like this? And if you do the average of this, you get 143.12. So if you look at where 143.12 is, it's up right here. So another fifth sample would, or fifth observation would basically be up in this 140 range, which is well inside the upper and lower control limits. So no problem. The process looks like it's under control. I say looks because we still want to look at the range. So the next thing we do is we calculate the range of the new observations, and you get 180 minus 98, so you get 82. Am I right? No, 190. Sorry, 190 minus 98 is 92. So you come over to the R chart, because R chart, you are plotting R. Just like X bar, you're plotting X bar. I can't say that enough because it becomes obvious to you when you realize the center line is the average of what you're plotting, and the data points are what you're plotting. So you look at this 92, and you come in here, and it's well within range right here. So you can conclude from that that your process is under control. In fact, if I'm looking at this from a manufacturing standpoint and from an operations director standpoint, this process is very well under control, because as you can see, your data is pretty well centered about the mean and very tight. So if this was a bell curve, this would be a narrow bell curve with a steep peak at the mean, because all the data is well centered around the mean. Let me go to the next example. So in this next example, which is to develop a proportion chart based on the exercise, and what this is a sample of 100 blood analyses taken a day randomly. So you can see each day there was 100 samples taken. And a P chart, some people call it a probability chart, which is incorrect. It's really a proportion chart, but it almost translates to a probability, because on day 1 you had 8 incorrect samples out of 100, which means you had a 0.08 probability, 8% probability of having an incorrect count. But that's also a proportion, because the sample size didn't necessarily need to be 100. It could have been 120 or some other number other than 100. So getting back to this, we look at the data for how many incorrect samples were taken each day for 20 days. We then table the proportion, which is basically the incorrect count divided by 100. So you'll see the proportion of 100 samples that were incorrect, and you'll see that the average proportion over 20 days of incorrect samples is 0.038. That becomes the mean P. And since this is a P chart, the mean P is going to be your center line. So you'll see across here 0.038 is used as your center line. The lower control limit is then calculated. Let me show you over here where that came from. The lower control limit of a P chart is basically calculated this way is upper and lower control limits. So it's the mean line of 0.038 plus 3 times the square root of the 0.038 times 1 minus 0.038 divided by 100. And then the lower control limit is just minus 3 sigma down. That was plus 3 sigma, that's minus 3 sigma. And you do the same thing. The mean P times 1 minus the mean P divided by 100. So let me get this chart off here without messing up everything and go back to this. So you can see the lower control limit. Like I said, if it comes out to minus some small number, it still needs to be truncated, rounded off to 0, only because you can't have a probability that's negative. So you just put zeros in here, and the upper control limit is calculated as plus 3 sigma using the 0.038. One thing I'll tell you, though, is what I noticed when I did this myself from the exercise is that they rounded off to 0.04 here. And if you round up to 0.04, you'll get a different upper control limit. When you're using so many decimal places, you get 0.098. But from a plotting standpoint, it'll look the same. So then to chart this, you highlight the data. You do insert line with markers, and then very easily you see the chart come up. If you notice, the follow-up question is going to say another 100 samples were taken with a 10% failure rate, which means 10 out of 100 equaled a p-value of 0.1, and that would be the 21st day, essentially, or whatever day that wound up being, and that would be 0.1, would be above your upper control limit. Therefore, the process is not in control because you already have a sample day that is beyond your upper and lower control limits. I will say, though, from as an operations director, if you see data like this even before you took your additional sample day, this is already out of control. Because even though they're within the upper control limits and the lower control limits, this is just all over the place. There's no consistency. And to use lessons in real life, if you go back to the data and you see you're getting incorrect counts anywhere from 0 and 1 and 2 all the way up to 10 and 9, that is a pretty wide range right there of incorrect counts out of 100 samples. You have some great days at 10 and 9 and some really horrible days at, some horrible days at 9 and 10 incorrect, and some really good days at 0 and 1. So even without looking at the next data point, you can see that this process needs corrective action. Another thing I'll tell you from a manufacturing standpoint, or even from a process capability standpoint, there's a parameter called CPK that you can look up. It's C sub P sub K, and it is key process capability is what that parameter indicates, and it's a measure of how centered about the mean you are and how close to the mean you are. So in the X and bar charts over here, these are pretty decent CPKs for that process. But when you look up here or down here at this P chart, you're going to get a very low CPK, which CPK of 2.0 is 6 sigma in the 6 sigma lean analysis methodology. But you're going to get a very low CPK here since you're basically all over the place and you don't have a very stable process. And again, corrective action needed because the very next one was even outside the control limit. In fact, that one's outside the control limit. So that is how the X bar, the R chart, and the P charts are calculated. If you have any questions, this is the actual homework assignment answer right here that you can compare to what you did and how you did it. If you have any questions whatsoever, please give me a call, email me, text me. Any way you want to get a hold of me, post a discussion post if you want all the students to see the question and answer so we can all share knowledge. That's great also. But But definitely get a hold of me if you're still not understanding this. This is an important part of statistical process control from a process standpoint, whether it be manufacturing process or making beds or taking blood tests or whatever the waiting on tables, whatever the samples you're taking and the data analysis that you're performing. This is a very important aspect of SPC to be able to track whether you have an in-control stable process or a very uncontrolled unstable process. Thank you and have a great day.